And this brings us to this very interesting and important graph. So let's look at the graph here. The y-axis is total number of cases, and the x-axis is percentage of travel routes we can close in an optimal world. So what we see here is that if we only close like 5% of the travel routes, we are actually going to get closer, actually very close to number of COVID cases, even if we close like 100% of travel routes. So this is really saying maybe closing all the routes is too much, and there's definitely some routes is more important than others. So now that we have the effect of number of migration on number of COVID, then we can move on to the social planners problem. And in economics, we call it social planner. It's just a different term to think about a benevolent society. And once we go to benevolent society, we need to take stance, what is benevolent society? And again, economics, traditionally, we take a utilitarian approach. That means we just aggregate everybody's preference together on the same unit. And here the unit is dollars. So what we are thinking is that, let's think of society is determine which routes to restrict so we can minimize the total cost of COVID infections across all cities and the cost of reduced economic activities from restricting migrations. So that kind of means we need to assign a dollar value on both the COVID infection as well as dollar value of restricting migrations on local economy. And here we have some key calibration parameters in this model. First of all, the paper assumed the total shutdown cost for intercity migration on economy is 40% of the GDP. So that means, I think that number comes from the observation that when Hubei closed down all its traffic from anywhere else, the economic activity shrink by 40%. So the assumption is if you close every single migration traffic routes, the GDP impact will be 40% of the city. And second is the assumption we make, the paper makes, is that the cost per infected person is about 1.6 million US dollars. Now, under those two assumptions, Dr. Chen and his co-authors can calculate what will be the optimal decisions. So this graph shows the 50 routes with the most positive difference between what they calculate and what's the reality. So what they observe is that some restrictions are more important than others, and the most important restrictions are those origin cities that have higher infections and closer to outbreaks. And second is that destination cities that have higher or larger population outflow. The first and second point make a lot of sense because the first point basically means the origin cities you have a lot of infected cases in the origin city. You probably don't want them to go out. And second is in the destination city, if a lot of people tend to move out of these destination cities, then people will actually just radiate across the whole nation. So you probably want to think about whether to restrict inputs in inflows into those destination cities. And third, as Dr. Chen previously pointed out, if all cities work together, so that's what you mean by under coordination, if all cities work together, it's usually more efficient and more effective than if every single city worked by itself. And interestingly, what they find is that if every city under coordination, a quick and stringent restriction for the outbreak city, it will allow for more relaxed restrictions in other cities.